Hey fellow nerds. So MOSFET, what does it do? Does it do things? Let's find out. We will begin with our idea on building an amplifier. We will learn the MOS structure, MOS operation, channel charge density, I-V characteristics of a MOSFET, and channel length modulation. Let us start with our ancient idea on how to build an amplifier. Assume we have an amplifier. We are giving an input V in. We are getting an output V out. The idea of the amplifier is that V output should be V input multiplied by something. We found that this is possible if we had a current source that was voltage controlled. For example, let us say we are getting a potential over here that is equal to V1. We have a current source over here whose value is I. Assume that the current provided by the current source I is K times V1, which means the current is proportional to V1, or we can say the current source is controlled by the voltage V1. The output is being taken across a resistor RL. The current that is flowing through RL is going to be I, and its direction is like this. If current is flowing in this direction through RL, that means RL has a positive potential over here and negative potential over here, because current always flows from positive potential to negative potential. But we are taking our output positive here and negative here. So V output is going to be negative of whatever is the potential we have across RL. According to Ohm's law, potential across RL will be IRL. So we can say V output is minus IRL, but I is KV1, so we can say V output is minus KVRL. In this particular case, you can see V1 is actually equal to V input. That means V output will be minus KRL multiplied by V input. Or output voltage is a constant multiplied by input voltage. Here we can write the voltage gain. Voltage gain, which is V output divided by V input, is minus KRL. So technically, to build an amplifier, all we need is a voltage controlled current source. We have already used one voltage controlled current source to build an amplifier. It was BJT, bipolar junction transistor. Today we'll get to know one more. Let us start by making some observations. This is the structure that we need. On top, we have a conductor plate. At the bottom, we have a semiconductor wafer. In between these two, we have an insulator, which is a dielectric. It is something that we use to fill the space between two plates of a capacitor so that its capacitance will increase. Now, width of the structure is W, length is L, and thickness of just the dielectric part is T. One more thing we have to make sure is that the semiconductor is p-doped so that the majority carriers are holes. Now, this is what we do. We will apply a potential V1 across it. The conductive plate will get the positive potential. Semiconductor will get the negative potential. Even though the semiconductor is p-doped and the majority carriers are holes, we know there are still going to be electrons, even though they are small in number. The negative potential that is applied on this side of the semiconductor will repel them. Or we can say the positive potential applied on the other side will attract them. This will make all the electrons go to this end of the semiconductor and get accumulated over here. This gives us a channel of free electrons at the interface of the semiconductor and the insulator. Let us write this down. When V1 is applied, electrons, which are the minority carriers in the semiconductor, accumulate as a channel at the semiconductor dielectric interface. Now, take a look at the structure again. Here we have a positively charged conductive plate, which can be considered as a layer of positive charge. On the other hand, here we have a layer of negative charge. In between, there is an insulator which is a dielectric. So basically we have a capacitor. Now We know capacitance is defined as A epsilon naught by T. A is the area of the plates. Epsilon naught is the permittivity of vacuum. T is the distance between the two plates. Here, the distance between the two plates will be the thickness of the dielectric, which we have already taken to be as T. If the width is W and the length is L, then the area can be taken as WL. Let it be there. How do we define the charge that is stored in the capacitor? It is CV. It is the product of the capacitance and the voltage that is applied across the capacitor. Here V1 is the applied potential. Out of V1, let us assume that V is dropped across the insulator so that the charge stored is CV. Anyway, we can see that if V1 is increased, V will increase. If V1 is decreased, V will decrease. Which basically means V1 or the applied voltage decides how much charge is stored in the capacitor. Or in other words, V1 controls how many electrons we get in the channel. Now let us write an expression for the charge density. Since this is a very thin channel, I am going to take the linear charge density. That is total charge divided by the length. It is very obvious that if V1 increases, the charge density also increases. My question is, does T has anything to do with the charge density? Well, you can see capacitance is inversely proportional to the thickness. So if the thickness is decreased, then the capacitance will increase. Now charge is CV. So if capacitance increases, then charge also increases. If charge increases, obviously charge density increases. So there are two ways in which we can increase the electron density in the channel. One is by increasing V1, the other is by decreasing T1. Keep this in mind. This is what we'll do next. We'll take a terminal on both sides of the channel. I'll call this point A and this point B. Now, between A and B, we will apply a potential V2 like this. Positive terminal of the cell is connected to A, negative terminal of the cell is connected to B. Now, what is going to happen? We know we have free electrons in the channel. The electrons will be attracted by the positive terminal of the cell and they will start flowing like this. Inside the semiconductor, they will be flowing from B to A. That means we have a current in the opposite direction, like this. Let us write this down. When V2 is applied, current flows from A to B. When I say current flows from A to B, I am talking about the direction of the current inside the semiconductor. Inside the semiconductor, current is flowing from A to B in this direction. But in the external circuit, you could say it is flowing from B to A like this. Now, we have already seen that if V1 increases, the density of electrons in the channel increases because charge is CV. If there are more free electrons available in the channel, then technically the resistance between the points A and B is decreasing. That means the current flowing between A and B will increase. So this is the conclusion we can make. V1 controls the current from A to B, which means what we have over here is nothing but a voltage dependent current source, which is exactly what we wanted. So the idea is pretty clear. For the conductive plate, we can actually use a metal plate. For the insulator, which is a dielectric, we usually use an oxide, for example, silicon dioxide. And for the semiconductor, we can use silicon. So technically, we have a metal, an oxide, and a semiconductor. MOS. Now, this structure is not very practical. You can see that two of our terminals are like this, on top and bottom. The two other terminals are on the sides. In the real world, we cannot have a device with its terminals all over its body. We need all the terminals on one side so that in an actual circuit, the connections with other devices can be made easily and efficiently. So what we have over here is not the actual MOS structure that we'll be using. You can just think of it as a prototype. We have to make a better version of this because connections cannot be made from the sides. Let me show you how. Let us take a metal plate. Now I'll take an oxide layer below that. Thickness of the oxide layer is TOX. Now below that we need a semiconductor that is P dot. Obviously the semiconductor part is wider than the other two parts. Now we'll make a heavily n-doped region over here and another one over here. This is the reason why we are doing it. We know when we apply a potential V1 like this, electrons will accumulate over here creating a channel. Once the channel is formed, we have to connect V2 between these 2 points. Right now, since we have two n plus regions on both sides of the channel, to connect the potential V2, all we have to do is take a terminal over here and take another terminal over here. V2 can be connected between these two terminals. Now when the channel is formed and V2 is connected, electrons will be flowing from this n plus region to this n plus region. Since this n plus region is providing the electrons, we can call it the source, and this will be our source terminal. Similarly, the electrons are being absorbed by this n plus region, so we can call it the drain, and this will be our drain terminal. We also have to apply V1 to the metal plate, so we'll take a terminal here also. Since voltage applied to the metal plate is what controls our current, we call it the gate. So this will be the gate terminal. So MOS structure has three terminals and the gate voltage controls the current between the source and the drain. The front view of a MOS structure looks like this. Now that we are familiar with the MOS structure, let us understand the MOS operation. First, we'll try this. We will keep the source voltage and the drain voltage to be 0 and then increase the gate voltage from 0. But to do all these, first we need a MOS structure. Now, to keep the source voltage and drain voltage 0, let us ground the source and drain terminals. We have to apply a voltage at the gate and increase it from 0. When VG is applied, we are giving positive potential over here. So for the semiconductor, it will be getting positive potential at this end. We know the semiconductor is p-doped, which means holes are the majority carriers. But when it gets positive potential over here, it will repel the holes and the holes will move from this end of the semiconductor to the other end. Which basically means the area closer to the end which has positive potential will get depleted of holes. That will give us a depletion region over here. Since the holes moved away, we'll have negatively charged ions in the depletion region. What else is going to happen? Like we have already seen, we are giving positive potential over here. So the electrons that are the minority carriers in the p substrate, they will all be attracted towards this end and they will get accumulated over here as a channel. Don't get confused. These are electrons and these are negatively charged ions. Now, one thing that needs to be very clear is that when gate voltage increases from 0, the channel does not immediately show up. At first, the holes are repelled and the depletion region is formed. Only when the gate voltage is sufficiently positive, the channel starts appearing. The minimum voltage that must be dropped across the semiconductor so that a conductive channel will be formed is called the threshold voltage. So as Vg increases from 0, holes move away from the oxide semiconductor junction, leaving the negative ions. There is no channel of electrons unless the gate voltage becomes greater than or equal to the threshold voltage. So when the gate voltage becomes greater than or equal to threshold voltage, that is when the channel starts to appear. What if you further increase gate voltage? We already saw if you increase it further, the electron density in the channel is going to increase. When electron density increases, technically the resistance between the source and drain is decreasing. Wait, does that mean the resistance between the source and drain is controlled by the gate voltage? Yes. Whatever we have between the source and drain right now can be modeled as a voltage controlled resistor. Something like this. Now let us try this. Source voltage and drain voltage are still zero, so the source and drain are still grounded. Gate voltage is not varying anymore, it is a constant, but it is greater than the threshold voltage, which means we have the channel over here. Now, my question is, will there be any current between the source and the drain? There won't be any current because, as you can see, source is grounded, drain is also grounded. Source and drain are at the same potential. We cannot have a current between two points that have the same potential. But we have already applied sufficient gate voltage. Our channel is ready. The only thing we need so that there is a current between the source and drain is a potential difference between the source and drain. So we can say the MOSFET is turned on, but there is no current because the drain and source are at the same potential. Now let us try this. Gate voltage is a constant, but it is greater than the threshold voltage, which means we have a channel that is ready. Since source voltage is supposed to be 0, I'll keep grounding the source. But the drain voltage has to be positive, so let us apply a positive potential over here. Now, before we do anything, let me explain to you something that we'll be following from now. You can see the gate has an applied voltage. Drain also has an applied voltage, but the source is grounded. Vg is applied between the gate and the ground. Vd is applied between the drain and the ground, but the source is grounded. So we can actually define Vg and Vd with respect to the source, since source is actually the ground here. We know Vg is the voltage at the gate with respect to the ground. Since source is at the ground, we can call Vg Vgs, meaning voltage at the ground with respect to the source. The same way, we'll be calling Vd Vds, meaning voltage at the drain with respect to the source. Now let us see what happens. These are the conditions we have. VGS is a constant and it is greater than the threshold voltage. Source is at the ground. VDS is now greater than 0. Let us start by assuming VDS is equal to 0. Initially, when you apply VGS, the gate voltage, all the holes here will be repelled. That will create a depletion region over here. Now, when VGS is further increased, specifically speaking, when VGS becomes greater than the threshold voltage, a channel of free electrons will be formed over here at the interface of the semiconductor and the oxide. We have already seen that the density of electrons in the channel depends on how much voltage we have applied at the gate. If the gate voltage is equal to threshold voltage, they will just start appearing. And if it is more than that, the charge density will also be more. Right now, VDS is 0, which basically means the drain and the source both are at 0 potential. So we could consider that over here in the entire surface we have 0 potential. What we have over here is a metal surface. So when you apply a potential VGS over there, the entire surface will get a potential VGS. So if I take over here, I have VGS 0. So the potential difference between these 2 points or the potential drop across the dielectric is VGS minus 0 or VGS. Over here, VGS 0. Over here, VGS 0. So the potential difference between the layer of positive charge and the layer of negative charge here is equal to VGS. It is a constant. Now let us apply a VDS that is greater than 0 and see what happens. Before we do that, I want to remove VGS. I will make sure VGS is equal to 0. Since VGS is 0, the channel will disappear and we will not have a depletion layer over here. I'm doing this just so that we can understand what VDS do to this. So I will make VDS greater than 0. The first and most important thing to understand here is VDS is being applied to a semiconductor. You are applying it over here. So at this end, you will get a potential VDS. On the other end, the potential is 0 because the source is grounded. So you have 0 volt here and VDS over here. In between these 2 points, voltage will be gradually increasing from 0 to VDS. If we plot it on a graph, this is how it will look like. On the x-axis, I have taken the position. On the y-axis, I have taken the potential drop. At this end, we get the maximum potential. It is VDS, the applied drain voltage. At the other end, we get the minimum voltage, 0. If you take any point in between, you can see that the voltage drop is gradually increasing from 0 to VDS. Now, to understand the concept that I'm trying to teach right now, it is better to take some values. Let us assume that VDS is 10 volt. Since we are applying 10 volt, at this end we'll get 10 volt. At this end we are getting 0 volt. Let us assume that over here we get a 7 volt. And at this point you get 3 volt. Now let us assume that the threshold voltage required is 2 volt. We have already kept VGS to be 0. I am going to make it 12 volt. Now VGS is being applied to a conducting metal plate. So if I apply a 12 volt, I am going to get 12 volt at all these points. So if I take this point, I have 12 volt over here and 10 volt over here. So the potential difference I get here is 2 volt. Similarly, over here, I get 12 minus 7, that is 5 volt. And over here, I'll get 12 minus 3, that is 9 volt. Finally, over at this end, it will be 12 minus 0, which is 12 volt itself. This is what we can conclude from here. Initially, when VDS was not applied, we were getting the same potential drop across all these points. But right now, potential drop is more at the source and it is less at the drain. And we know this potential drop is what determines the charge density in the channel. The first thing is it has to be greater than the threshold voltage. If it is even more than that, the channel charge density will be more. You can see that at this end, the potential difference is actually 2 volt, which is just equal to the threshold voltage. So at this end, the channel will just start to appear. But at this end, we have 12 volt, which is really high. So the charge density is going to be really high. This means the channel we will get right now will not be uniformly distributed. Instead, it will look like this. You can see how the charge density decreases as we go from the source to the drain. In fact, at the drain end, in this example, what we have is 2 volt, which is actually equal to the threshold voltage. So over here, as you can see, the channel is just being formed. We can also plot the variation of charge density with respect to x-axis. This is how it will look like. It is maximum at the source end and it is minimum at the drain end. In between, it is gradually decreasing. So this is the observation we can make. When VDS is applied, the channel gets more positive potential on the drain side than the source side. Because of this, the potential difference will be larger on the source side and that will make more electrons accumulate on the source side. Now that this concept is clear, let us move further. We have applied VDS now, giving a positive potential over here. So these electrons in the channel will be attracted by VDS and they will flow like this in this direction, which means we'll have a current in the opposite direction. Let's mark the current as ID. ID is the drain current. Now, electrons are flowing from the source to the drain in this direction, which basically means we have a current over here. Let's mark it as the source current. Now, whatever is the number of electrons that flow out of the source per second is exactly what comes to the drain per second. So, ID is actually equal to IS. Let's write this down. When VDS is applied, a current starts flowing from the drain to the source, and the source current is equal to the drain current. How about the gate current? Is there a gate current? See, the gate voltage is applied to a metal plate over here. And in between the metal plate and the semiconductor, we have an insulator. So current cannot pass through it, which means there is no gate current. Gate current is zero since the metal plate is connected to an insulator. Now that we have a better understanding of how the MOS structure operates, let us have our final note. We know that the drain current is controlled by our gate voltage. Because when you increase the gate voltage, the channel charge density will increase and therefore the current will also increase. When we apply the gate voltage, we get positive potential over here. Compared to that, we can say we get negative potential over here. This is a semiconductor that is p-doped. Even if it is p-doped, it will have many electrons that are the minority carriers. When we have a positive potential here and a negative potential here, that essentially creates an electric field in this direction. Direction of electric field is always from the positive potential to the negative potential. Now, the free electrons, which are the minority carriers, are negatively charged. So the electric field will apply a force on them that is in the opposite direction like this. And this force is what makes all the free electrons accumulate as a channel over here. So technically, the flow of the drain current is controlled by an electric field that is induced by the gate voltage. Because of that reason, we can call this a field effect transistor. And in this particular field effect transistor, we are using a MOS structure. MOS stands for metal oxide semiconductor. So what we have over here is a metal oxide semiconductor field effect transistor or a MOSFET. I guess now the hard part is over. We all understand how the MOS structure is formed and how it operates. So let us move on to the easier side, mathematics. Before that, let us define the dimensions of a MOSFET. As we have already seen, thickness of the oxide layer is taken to be T-ox. Width is W. Length of the metal plate is taken to be L. This will also be the length of the dielectric part. But if you take a closer look, you can see that the source over here and the drain over here are overlapping with the dielectric part a little bit. Now this is required because when the channel is formed, we'll have a better electrical connection between the source and the channel and the drain and the channel. But the consequence of this overlapping is now we'll have to take the effective length between these 2 points. So let us mark that as our effective length. Let us move on to the mathematics of this and find an expression for the channel charge density when the gate voltage is greater than the threshold voltage and drain voltage is 0. Since the drain voltage is 0, we'll have a channel that is uniformly distributed. Channel charge density is also going to be uniform. We have a layer of positive charge over here. We have a layer of negative charge over here. These two are separated by a distance which is equal to the thickness of the oxide layer. So what we have over here is a capacitor. Let us start by defining Cox to be the capacitance per unit area. In that case, what will be the total charge stored in this capacitor? Total charge stored in any capacitor is the product of the capacitance and the voltage drop across the two plates. So here we can define it like this. Total charge in the channel is C multiplied by V. Now what is C? We defined C aux to be the capacitance per unit area. C is the actual capacitance, so that will be C aux multiplied by the area. If the width is taken to be W and the effective length is L, then the area will be WL. So here for C, we can write C aux multiplied by the area, which is WL. Now this has to be multiplied with whatever is the voltage drop we have across the oxide layer. We are applying VGS over here. Out of that, the threshold voltage will be dropped across the semiconductor so that the channel is formed. The rest will be dropped over here across our capacitor. So the voltage drop across the capacitor is VGS minus VTH. VGS minus VTH can be called the overdrive voltage. Now this is the total charge. What we want is the channel charge density. When we say channel charge density, we are actually talking about the linear charge density. That is total charge in the channel divided by the length of the channel. If we divide this expression with L, L and L will get cancelled and we'll get the channel charge density to be WC aux multiplied by VGS minus VTH. Keep in mind that if the gate voltage is less than the threshold voltage, no channel will be formed. Charge will be equal to 0. Again, from this expression we can see that for a constant VGS, the channel charge density is going to be a constant, which means we'll have the same charge density throughout the channel. Now, let us find an expression for the channel charge density when VDS is not 0 anymore. We already saw what happens when we apply VDS. We will get an extra potential drop across the channel and it increases from 0 to the maximum from the source to the drain. Let us say that at a particular point on the x-axis, the potential drop due to the drain voltage is V of x. We apply VGS over here. Out of that, the threshold voltage will be dropped across the semiconductor. So the effective gate voltage that we get across the capacitance is VGS minus VTH. On top of that, we have V of x on the other side also. So the net voltage drop across the capacitance is going to be VGS minus VTH minus V of x. So we can modify the previous equation like this. Channel charge density will be WCOX, which is the capacitance, multiplied by overdrive voltage will be VGS minus VTH minus V of x. Let's put this in a box. We know V of x will be the highest over here near to the drain because VDS is being applied at the drain. It will be the lowest over here at the source because at source we basically have 0 voltage. At the source, V of x is 0, so this term will vanish and we'll get the channel charge density to be WCOX VGS minus VTH, which is the maximum value. At the drain, V of x will be the maximum and we are subtracting V of x from our original overdrive voltage. So the channel charge density will become the smallest. So we can say the channel charge density varies with x. We have already seen the theoretical aspect of this. We even plotted a graph of variation of charge density with respect to x. Now we also have the math. Now let's try to use the expression for channel charge density to find an expression for our drain current. To do that, first let us assume that the electrons are moving at a speed of V meter per second, which basically means that they cover V meters in 1 second. I want to know how much charge flows in 1 second because charge per second is the drain current. So all I have to know is how much charge is in V meters because then that much charge will be flowing in 1 second. So to find how much charge is there in V meters, Let us take V meters from the channel. We already know the channel charge density. And what we have is the linear charge density. It is total charge divided by length. So it is very easy for us to find out how much charge is there in V length, because it is going to be linear charge density multiplied by the length V. That will be the amount of charge we have in V. That means that will be the amount of charge that is flowing in 1 second. Let us write this down. Total charge in V length is going to be linear charge density multiplied by the length V. We already found the expression for linear charge density. Since we have also applied VDS, the charge density is going to be WCOX multiplied by VGS minus VTH minus V of X. Now this is to be multiplied with V. V here is the velocity of the electrons. Now, like we already said, this is going to be the amount of charge that flows in 1 second. Let me try to convince you that this expression that we have over here is actually charge per second or current in one more way by using dimensions. We know this much is the linear charge density. So its dimensions are going to be dimensions of charge divided by dimensions of length. This is being multiplied by velocity. Dimensions of velocity are dimensions of length divided by that of time. Now L and L gets cancelled. What we have over here is charge by time. So yes, what we have over here is the total charge that flows in 1 second. But charge per second is what we call current. So what we have over here is our drain current ID. ID is WCOX multiplied by VGS minus VTS minus V of X multiplied by the velocity V. Again, the V over here is the velocity of an electron. But we can define the velocity of an electron like this. It is negative of mobility of an electron multiplied by the electric field. Now, which electric field are we talking about? We are talking about the electric field that will exert a force on these electrons, forcing them to move from the source to the drain in this direction. Well, we know VDS is what is making these electrons move from here to here. So this electric field is provided by VDS. For example, if I take a random point X over here, VDS will be providing a potential V of X there. Because of that, we'll have a potential E of X there. This is the electric field that will force the electrons to flow. Now, what is the relation between electric field and potential? E is given as negative dV by dx. Electric field is the negative of potential gradient. So we can write V like this. V is negative mu n multiplied by negative of dV by dx. Here mu n is the mobility of electron. Yellow colored V is the velocity of electron. Blue colored V is the potential we have at a random point X. We can call it V of X, potential as a function of X. Let us replace V over here in this equation with minus mu n multiplied by minus dV by dx. Well, we don't have to write two negatives. They'll get cancelled and we'll have mu n dV by dx. Then the equation of drain current will look like this. WCOX, VGS minus VTH minus V of X multiplied by mu n dV by dx. Now, we said V in dV by dx is actually V of X itself. In this equation, we have a V of X here also. So there is no point in calling it V of X here and V here. So I'm going to call it V in both these places. Instead of writing V of X, I will just write it V. But you have to know I'm talking about V of X. So we got ID is WCOX multiplied by VGS minus VTH minus V multiplied by mu n dV by dx. Now, this is not the proper equation for drain current because we have a dV by dx over here. We don't know what it is right now. So, I'm going to take dx to the other side of the equation and put it along with id. Then we get id dx is W Cox multiplied by Vgs minus Vth minus V multiplied by mu n dV. We have a dx over here and we have a dV over here. So let us integrate both sides of the equation. How do we define the limit of the integration? On the left hand side, the variable with respect to which we are doing the integration is x, and x varies from 0 to L. So we'll integrate from 0 to L. On the right hand side, the variable with respect to which we are doing the integration is v of x. When x is 0, v of x is 0. When x is L, v of x is the maximum VDS. So the limits of integration on the right hand side will be from 0 to the maximum VDS. Let's do the integration. ID does not have anything to do with the variable x. So let us take ID out of the integration. Now what we have over here is integral dx. Integral dx is x. Limit is from 0 to L. So this is L minus 0 or just L. So on the left hand side, we get ID multiplied by L. We have to do the integration on the right hand side. The first thing is W, Cox and mu n. These doesn't have anything to do with V, which is the variable with respect to which we're doing the integration. So W, Cox and mu n can come out of the integration. Now here I have integral of Vgs minus Vth minus V multiplied by dV. I am going to split it into two. First I will do integral of Vgs minus Vth dV minus integral of V dV. Then this is what we get. Let us do this integration first. We have Vgs minus Vth. Both of these does not have anything to do with V of x. So we can take it out of the integration. That gives us integral dv. Integral dv is v. Limit is from 0 to vds. So it will be vds minus 0 or vds. So we can replace this part with just vds. The second integration we have is integral v dv. Integral v dv is v square divided by 2. Limit is from 0 to VDS. So this will be VDS square by 2 minus 0 or simply VDS squared divided by 2. So we can replace this much with VDS squared divided by 2. This gives us ID multiplied by L is W mu n Cox multiplied by VGS minus VTH multiplied by VDS minus VDS squared divided by 2. What we want is an expression for the drain current ID. All we have to do is take L to the other side of the equation. Then we get this. Here W and L are the dimensions of the MOSFET. It is usually given as a ratio W by L. For example, W by L is 20. So I will modify the equation and write it like this. ID is mu n Cox times W by L multiplied by VGS minus VTH times VDS minus VDS square divided by 2. This is our final equation for the drain current. Let us put it in a box. Now let us try to plot the I-V characteristics using the expression for drain current we just found. First, let us take what is the drain current if VDS is not applied. That means VDS is 0. If VDS is 0, this term will become 0. This term also becomes 0. Basically, ID will be 0, which is something we already know. So if VDS is 0, the plot of drain current versus gate voltage will look like this. There is 0 current. We know the channel will be formed when VGS is greater than the threshold voltage. But unless VDS is applied, there will be no current. So we can say the device is on when VGS is greater than the threshold voltage, but current is 0 as long as VDS is 0. Let us now try to plot the variation of drain current with respect to the drain voltage. We already have an equation of ID versus VDS. ID is a constant multiplied by another constant multiplied by VDS minus VDS square by 2. Let us call this constant K1 and this constant K. I'll also call VDS X. Since ID is being taken on the y-axis, I'll also call it Y. Now the equation becomes like this. Y is K1 multiplied by Kx minus x square by 2. Opening the bracket, I can write it like this. K1 Kx minus K1 by 2 x square. Now K1 multiplied by K is a constant, I'll call it C1. K1 by 2 is also a constant, I'll call it C. Then the equation becomes Y is equal to negative Cx square plus C1x. This is obviously a quadratic equation, and the graph of a quadratic equation is always a parabola. Now the question is, what kind of a parabola will it be? Since the equation is of the form y equals something x square, the graph is going to be symmetric with respect to a vertical line. So either something like this or something like this. Here the coefficient of x square is negative, so our graph is supposed to look like this. Let us write this down. Since this is a quadratic equation, the graph will be parabolic. Also, since the equation is of the form y equals something x square and the coefficient of x square is negative, the graph is going to be of this form. Now, since we have already learned the operation of a MOSFET, we know if we increase VDS, obviously the current has to increase. But a parabolic graph increases from 0 to maximum and then it goes back to 0. Do you think if we keep increasing VDS, at some point the current will decrease and go back to 0? That seems unlikely, but it is obvious that the current has to increase when we increase VDS. So let us take only the first half of the parabolic path and analyze that. Later we'll analyze what happens after it reaches the maximum value. So for the first half of the parabola, our graph will look like this. This is the maximum value our current gets. I want to know what is the value of VDS that I have to apply so that I get the maximum value of drain current. That's easy to find because I have the expression for ID in terms of VDS. If I find dID divided by dVDS, since I am taking ID on the y-axis and VDS on the x-axis, this is basically dy by dx or the slope of the graph. What is the slope of the graph at the maximum point? This is the maximum point. If I draw a tangent line at the maximum point, it is a horizontal line. Its slope is equal to 0. So when ID gets maximum, dID by dVDS or the slope will be equal to 0. This is the idea using which we'll find the value of VDS when ID becomes maximum. ID is maximum when dID by dVDS is equal to 0. To make the math of finding dID by dVDS simple, I am going to keep calling this constant K1, this constant K, VDS X, and ID Y. So to find dID by dVDS, I have to find d by dx of K1 multiplied by Kx minus x square by 2. Here we have K1 multiplied by Kx minus half x square. We can write it as K1 Kx minus K1 by 2 x square. We can find the derivative of these two terms with respect to x separately. D by dx of K1 Kx minus d by dx of K1 by 2 x square. D by dx of K1 Kx. K1 and K are constants. So this is actually K1, K multiplied by d by dx of x. D by dx of x is 1. So this is simply K1 multiplied by K minus d by dx of K1 by 2 x square. Again, K1 by 2 is a constant. So this is actually K1 by 2 multiplied by d by dx of x square. Derivative of x square with respect to x is 2x. So this is actually k1 by 2 multiplied by 2x. 2 and 2 gets cancelled. It is k1x. So we get k1k minus k1x is equal to 0. Here k1 is w mu n cox divided by L. It is obviously not 0. Since k1 is not 0, over here in this equation, we can cancel k1 in both these terms. That will give us k minus x is equal to 0. So the drain current is maximum when k minus x is equal to 0 or when x is equal to k. Now, what is x? X is VDS. What is k? K is VGS minus VTH. That means the drain current is maximum when VDS is equal to VGS minus VTH. We can mark this point over here as VGS minus VTH. Let us also find out an expression for the maximum value of drain current. Drain current is maximum when VDS is equal to VGS minus VTH. So to get the maximum value of drain current, all I have to do is replace VDS in this equation with VGS minus VTH. This is the equation we get. Maximum value of ID is mu n Cox W by L multiplied by VGS minus VTH multiplied by VGS minus VTH itself minus VGS minus VTH squared divided by 2. Here VGS minus VTH multiplied by VGS minus VTH will become VGS minus VTH squared. Now this is actually k square minus k square divided by 2, which is k square divided by 2. So we get mu n Cox W by L VGS minus VTH squared divided by 2. Or we can write ID max is half mu n Cox W by L VGS minus VTH squared. Let's put this in a box. Let us try something else. We have the expression for drain current over here. Inside the bracket, we have VGS minus VTH multiplied by VDS minus VDS squared divided by 2. I am going to take VDS by 2 as common from it. If I take VDS by 2 from this term, it will become VGS minus VTH multiplied by 2. If I take VDS by 2 from this term, it will become VDS. So I can write the expression like this. Now I want to find out the drain current if VDS is very much less than 2 times VGS minus VTH. Because inside the bracket over here, we have 2 times VGS minus VTH minus VDS. Now, if VDS is very much smaller than 2 times VGS minus VTH, I can say this whole thing is approximately equal to just 2 times VGS minus VTH. Because VDS is very small and we can ignore it. So we can write ID is approximately mu n Cox W by L VDS by 2 multiplied by just 2 times VGS minus VTH. Here 2 and 2 gets cancelled. Then ID becomes mu n Cox W by L VGS minus VTH multiplied by VDS. Mu n is a constant. Cox is a constant. W by L is a constant. We have also taken VGS to be a constant, so VGS minus VTH is also a constant. So if we check the relation between ID and VDS right now, we can see that ID is a constant multiplied by VDS, which means ID is proportional to VDS. And if we draw the graph of ID versus VDS, this constant will be the slope. A graph with a constant slope is a straight line graph. We can actually observe that over here in this graph. When VDS is really small, the graph is almost a straight line. So we can write for VDS being very much smaller than 2 times VGS minus VTH, ID versus VDS graph is a straight line and the slope is mu n Cox W by L VGS minus VTH. So basically, mu n Cox W by L multiplied by VGS minus VTH is the slope of an IV graph. According to Ohm's law, what will be the slope of an IV graph? Slope of an IV graph will be I divided by V because I is taken on the y-axis, V is taken on the x-axis. I by V according to Ohm's law is 1 by R. So we can say when VDS is very much less than 2 times VGS minus VTH, the resistance of the channel between the source and the drain is 1 by mu n Cox W by L VGS minus VTH. Therefore, we can say that a MOSFET acts as a voltage dependent resistor if VDS is very much less than 2 VGS minus VTH. Now that we're trying to figure out the mathematics for every concept we learned in the first half of the video, let us bring back this example. We gave a 10 volt at the drain and 12 volt at the gate. Threshold voltage was taken to be 2 volt. Since 10 volt is being applied over here, at this end we got 10 volt itself. Over here we got only 7 volt. Over here we got 3 volt. And at the source end we got 0 volt. So at this point the potential drop was 12 minus 10, which is 2 volt. At this point it was 12 minus 7, which is 5 volt. At this point it was 12 minus 3, which is 9 volt. At this point it was 12 minus 0, which is 12 volt. Now at the point that is closest to the drain, we got 2 volt, which is exactly equal to the threshold voltage, which is the minimum voltage required for the channel to form. So we said the channel just started appearing over here. Now my question is, what if instead of 10 volt, VDS was 12 volt? Then the potential here will be 12 instead of 10. Potentials at these points will also increase accordingly. Instead of 7, let us say we get 10 over here. Instead of 3, let us say we get 5 over here. So at this end, voltage difference becomes 12 minus 12, that is 0 volt. At this point, it becomes 12 minus 10, that is 2 volt. At this point, it becomes 12 minus 5, that is 7 volt. And finally, over this end, we still have 12 minus 0, which is 12 itself. Now, this is the problem. Check out this point. Here we are getting 0 volt, which is obviously less than the threshold voltage. Threshold voltage is the minimum voltage drop we need so that the channel will be formed. And over here, it is less than that, so the channel cannot form. In fact, if you take a look at this point, you can see the voltage drop is 2 volt, which is exactly equal to the threshold voltage. So between these 2 points, obviously the potential drop is going to be less than 2 volt. It is going to be less than the threshold voltage, so the channel will not be formed there. Channel will only be formed up to this point, because this is where we get the minimum required voltage drop. This is called pinch off. In this example, pinch off happened at this point. So the idea is this. For the channel to be formed, potential difference between the gate and the oxide silicon interface should be greater than or equal to the threshold voltage. That means VGS minus potential dropped at that point due to VDS should be greater than or equal to the threshold voltage. Or we can write potential drop due to VDS at that particular point should be less than or equal to VGS minus VTH. If this is not the case, we will not have enough potential drop and the channel will not be formed there. So for channel to be formed, V of x has to be less than or equal to VGS minus VTH. So we can say at all these points, V of x is less than VGS minus VTH. And at all these points, it is greater than VGS minus VTH. Which means it is at this point that V of x is equal to VGS minus VTH. So we can say pinch off happens wherever V of x is equal to VGS minus VTH. Now let us take the case where VDS is actually greater than or equal to VGS minus VTH. In that case, pinch off might happen and we can visualize it like this. Let us assume that it is at this point that V of x became just equal to VGS minus VTH and this is where the pinch off happened. At all these points, it is greater than VGS minus VTH, so we do not have a channel, and at all these points, it is less than that, so we do have a channel. We already know there is a depletion region that is formed over here. Let us also show that. Now, what I want to find out is what happens to the drain current ID when VDS is greater than or equal to VGS minus VTH. Because if you remember this, we have already plotted a graph of ID versus VDS and we saw what happens to ID when VDS increases from 0 up to VGS minus VTH. We still have no idea what happens to the drain current when VDS increases from VGS minus VTH. So let us find it now. I am going to derive the drain current again according to the current conditions. Earlier, we found an expression for the drain current by doing this integration. On the left hand side, we integrated from 0 to L. On the right hand side, we integrated from 0 to VDS. To rederive ID according to the present conditions, the only difference I have to make is to the limits of the integration. On the right hand side, instead of integrating from 0 to VDS, I'll be integrating from 0 to the potential at this point, which is VGS minus VTH. Because right now the channel only exists from here to here. So let us change it. On the left hand side, we integrated from 0 to L. L is the length of the channel. From the figure, we can see that the effective length of the channel is smaller now. But let us ignore that for now. We'll assume that the difference is very small, that we'll still integrate from 0 to L on the left hand side. So everything is the same except the limits of integration. On the left hand side, ID is a constant with respect to the variable x. So ID can be taken out of the integration, which gives us ID integral from 0 to L dx. Integral dx is x. Giving the limits, we get L. So this becomes ID multiplied by L. On the right hand side, W, mu and Cox doesn't have anything to do with the variable V, so we can take it out of the integration. Now, we have VGS minus VTH minus V. I'm going to separate it. I'll write integral VGS minus VTH dV minus integral V dV. This is exactly what we did earlier. The only difference is the limit. Now the first integration is integral VGS minus VTH multiplied by dV. Here the V in the dV, if you remember, it is V of x. It depends on VDS. So VGS does not have anything to do with the variable V. That means VGS minus VTH can be taken out of the integration. Now here we have integral dV. Integral dV is V. Limit is from 0 to VGS minus VTH. So this whole thing will simply become VGS minus VTH. Here we have integral V dV. Integral V dV is V square by 2. limit is from 0 to VGS minus VTH. So it will become VGS minus VTH squared divided by 2. The equation will become like this. Again, VGS minus VTH multiplied by VGS minus VTH is VGS minus VTH squared. So this is like k square minus k square divided by 2, which is k square by 2. Now, if we want an expression for ID, all we have to do is take L from the left hand side and put it over here in the right hand side. Then we get an expression for ID like this. Half mu n Cox W by L VGS minus VTH whole square. But this is exactly what we got over here when VDS is equal to VGS VTH. This is the maximum value of ID that we got. Does that mean once the pinch off happens at VDS being equal to VGS minus VTH, the current is a constant? Well, mathematically, it looks like it. Let's put the equation in a box. Once VDS is greater than or equal to VGS minus VTH, ID does not depend on VDS anymore. There is no VDS in this equation. So we can say the current becomes constant. The mathematics is convincing, but this doesn't make sense, does it? For example, in this figure, the pinch off is happening over here. Now, if I increase VDS, the pinch off will happen somewhere over here. If I decrease it, pinch off will happen somewhere over here. According to the equation, as long as VDS is greater than VGS minus VTH, it does not affect the drain current. So according to the equation, even if the pinch off happens over here, or over here, or over here, the drain current is the same, which doesn't make sense, does it? Well, let us understand why it is so. Assume that at this point V of x became just equal to VGS minus VTH and the pinch off happened over here. That means in this gap we simply have the depletion region. Now assume that we increased VDS and pinch off is happening at this point instead of this point. Now when this happens, the length of the depletion region increases. That means the resistance these electrons have to overcome increases. But VDS is also increased, isn't it? So VDS will be pulling these electrons with better strength. That means the current can still be the same. To better understand this concept, let us take Ohm's law. V is equal to IR. Now assume that the resistance changes proportional to voltage. When voltage increases, resistance also increases. When voltage decreases, resistance also decreases. So the ratio V by R is going to be a constant. But V by R is I, so I is going to be a constant. This is exactly what is happening here. When VDS increases, length of the depletion region increases, which means the resistance here increases. Now, increase in R is proportional to the increase in VDS, which means the current can remain the same. Electrons in the channel are free to move out of the channel through the depletion region if it is attracted to the drain by VDS. The depletion region is free of electrons and it has a resistance. Now, if there is an increase in VDS, distance from the drain to the pinch off will increase and therefore the resistance will also increase. But the increase in resistance is due to the increase in VDS. Resistance increases in proportional to the applied VDS, which means the current will remain constant. Using this idea, let us complete our ID versus VDS graph. We already found that when VDS is less than VGS minus VTH, ID increases with VDS. When VDS becomes equal to VGS minus VTH, we get our maximum value. Now, when VDS becomes greater than VGS minus VTH, the current will be a constant, and that constant will be equal to the maximum value of ID. So the graph will look like this. So when VDS is greater than VGS minus VTH, we get a constant current. So we call this the saturation region. Also, over here, we already saw the graph is almost a straight line, so we can call that the linear or the triode region. We saw that when VDS becomes greater than or equal to VGS minus VTH, the drain current takes its maximum value and becomes constant. Maximum drain current is given by the expression half mu n Cox W by L VGS minus VTH whole square. Obviously, there is no VDS in this equation, so the current does not depend on VDS anymore. But we have VGS over here. So if we plot the variation in the maximum value of drain current against VGS, we get a graph that looks like this. Obviously, until VGS becomes at least equal to the threshold voltage, current will be zero, but after that it increases like this. Let us solve a problem now. We have to design a 1 milliampere current source. A current source is supposed to give us a constant current. From the I-V characteristics, we can see that a MOSFET gives us constant current in the saturation region. And in the saturation region, current is the maximum value. So to design the current source, we can use this expression. This is the expression for the maximum value of current. Half mu n Cox W by L VGS minus VTH whole square. Mu n Cox is given. Threshold voltage is given. W by L is also given. All we have to do is substitute the values and find out what is VGS for ID being 1 milliampere. If we do that, we get VGS is 1.9 volt. Now, let us give some validation to something that we overlooked before. It is related to pinch off. If you remember this, when I re-derived ID at pinch off, I changed the limit of integration on the right hand side of the equation. Instead of writing VDS, I wrote VGS minus VTH. But on the left hand side, I still wrote L. But this is not technically correct, is it? L is the effective length of the channel. But right now, since pinch off is happening over here, the effective length of the channel will decrease. Since L comes in the denominator of the current equation, the current should increase. If we also include that, we'll have to modify the equation like this. The new equation for ID will be half mu n Cox W by L VGS minus VTH whole square multiplied by 1 plus lambda VDS. Basically, as VDS increases, effective length of the channel decreases. So to show the dependence, we have to multiply the drain current with the factor 1 plus lambda VDS. This phenomenon is called channel length modulation, and lambda is the channel length modulation coefficient. Here, lambda is being multiplied with VDS and then it is added to a constant. A constant is dimensionless, so if lambda VDS is being added to a constant, that means lambda VDS should also be dimensionless. So dimensions of lambda will be the reciprocal of dimensions of voltage, and its unit will be volt inverse. So if we include channel length modulation, the graph of ID versus VDS will look like this. ID does not become constant after VDS becomes greater than VGS minus VTH. Instead, it slightly increases linearly. Throughout this video, we have taken the semiconductor part of our MOSFET to be p-doped. And the channel is made of electrons. Since the channel is of n-type, we call this n-MOSFET. Now, if the semiconductor were n-doped and the channel were made of holes, then we could call this a p-MOSFET. Before we move on further, there is one question I want to answer. We made the semiconductor p-doped. That means the majority carriers here are the holes. Electrons are minority carriers. And the minority carriers are making the channel. Now, if we needed electrons to make the channel, why did we not make this n-doped so we have a lot of electrons available? The reason is simple. If this were n-doped, then the majority carriers will be electrons. That means we'll have lots of electrons in the substrate. In that case, we will not be able to make a well-defined channel of electrons over here. There will be electrons everywhere. The circuit symbol of an n-MOSFET looks like this, and for a p-MOSFET, it looks like this. In the n-MOSFET, you can see current is flowing from the drain to the source. In p-MOSFET, it is from source to drain. That is because in n-MOSFET, the channel is made of electrons. So direction of current will be the opposite of the direction of flow of charge carriers. But in p-MOSFET, channel is made of holes. So direction of current is the same as direction of flow of charge carriers. Now before we end the video, let's make a simple model of a MOSFET that is in saturation. I have a MOSFET over here. Source is grounded. Between the gate and source, I have applied VGS. Between the drain and the source, we have VDS, and we have made sure that VDS is greater than VGS minus VTH so that the MOSFET is in saturation. Now, when MOSFET is in saturation, we get a constant drain current. So we have current ID flowing over here, and it is a constant. The saturation current is given by the expression half mu n C ox W by L VGS minus VTH whole square. Obviously, this does not depend on VDS anymore, but it depends on VGS. So this is a voltage controlled current source. Which voltage is controlling which current? VGS can control ID. So if we make a simple model of this MOSFET, this is how it will look like. We have a dependent current source. Whatever is the voltage we get between the gate and the source determines the value of current. Because the current is half mu n C ox W by L VGS minus VTH whole square. So that's all about it for today. See you in the next video. And please don't forget to subscribe.